Thank you. First of all, I want to thank the organizers for this opportunity to give this talk here. It's a great pleasure, a great honor, and also it's really quite a special place in PA. It's my fourth time here, and I must say I value this place very much. So I'm definitely very pleased to have this opportunity to speak here. Right, so what I want to talk about today is a topic which has to do with probability theory and which mixes kind of two worlds. And the worlds are in questions are on the one hand random walks and on the other hand percolation theory. And the issue which is more or less at stake there is how can paths of random walks create large separating interfaces in high-dimensional spaces. Okay? So it's going to be a bit clearer what I want to aim at, and I'm going to discuss a problem where these kind of ideas have been investigated with more detail. So that's the disconnection of discrete cylinders. So the setup is the following. You have a cylinder which is discrete, which has a base which is a large d-dimensional torus, so large, the side length is n. And for the time being, the dimension d of the base is bigger or equal to 1, but in fact, I'm not interested in the case d equal 1. I will be mostly interested in d bigger or equal to 2. That will be part of these large dimensional spaces I was talking about. And the problem is the following. You consider the random walk on the cylinder. What does that mean? It means that you have a motion, so you have a particle starting at a point, and it picks one of the neighbors in the cylinders at random, say x1. And then again, it picks again at random another neighbor, and it moves along, and it makes this kind of weird-looking trajectory. And now the kind of question that you want to understand is what's the behavior of the disconnection time of this random walk for the cylinder. So what you mean by that is you want to look at the smallest n such that this collection, this trajectory up to time n, x0, x1, x2, xn, disconnects En. So what does that mean, disconnects En? It means that there is no way to draw a path from the top end to the bottom end of the cylinder without meeting this red path of the walk here. So why on earth should you wonder about such a quantity like that? So this question came in fact from theoretical physics. So that came from a theoretical physicist Hilhorst, who is at Orsay in Paris, near Paris. I should not say Orsay in Paris, but near Paris. And he was wondering about that question because for him, this random walk was somehow modeling a toy model for a damage created by some kind of erosion catalyst. So it's a kind of damage which is created in a material. So you can think of a termite in a wooden beam. And the question here is, when does the damage become sizable? And one way to say sizable, it's to the extent that it's macroscopic. And if you pull apart these two ends, well, the material is just breaking. So this is the disconnection time. And so how large is this Tn? But companion questions to that is, well, can you say anything where the disconnection happens? And also, what's the appearance of the material at the time of the break? Okay. Now, it may be, and I don't want to be arrogant, but it may be that you have not been constantly thinking about this question. And for this reason, I just want to show you a picture of that will somehow set your intuition in the right mode. So So this is something that has been a simulation by a former student of mine, Laurent Gergen. And what you are seeing here is somehow this, not the path of the walk. What you are seeing here is the material that remains on the bottom part at the time of the break. And so maybe to have some idea of a bit of how it looks. So you see here you have a rather delicate structure which is here around the point of break. All right, so in some sense the stake here is to have some idea of what kind of object we are talking about. All right, so first of all, why is it that the walk disconnects? So there are two simple bounds, very simple-minded bounds that you can give. And the first bound is to say that somehow if the walk is covering one floor, say the floor 0 where it starts, so if it has visited every point, then disconnection has occurred. And since you are in a structure here where the walk is recurrent because somehow it's essentially a one-dimensional motion which is taken, that will happen sometime. Another kind of easy bound is that to be able to disconnect, it should be that the projection on the base is somehow covering every point of the base. Otherwise, you just put an infinite straight line which will not meet the path of the walk. So this is, in a sense, the nature of these bounds, which is here. If you have Cn, which is what is called the cover time of the 0 floor of the cylinder by the walk, so the disconnection time is less than Cn. And if you look at the cover time of the base by the projection on the base of the walk, well, you have the fact that the disconnection time is bigger than Cn tilde. Now, one of these two quantities has been very much investigated in the literature, and that's essentially the Cn tilde. So this is a kind of classical cover time question, and it's known since '83 that Cn tilde in rough order behaves like n to the d, at least when d is at least 2. And for me, I'm really interested in d at least 2. And in fact, much more is known. It's known that there is a logarithmic correction to nd, and the constant in front of the logarithmic correction is even known. So a lot of things are known about it. Now, the natural question is, these are very silly, very simple-minded bounds, from above, from below. Is any one of the two capturing any truth about the object of interest? And, well, you can pick your guess. And what happens is that the time to disconnect the 0 floor is, in a sense, something which captures the principal order of this disconnection time. So this is a result of Amir Dembo and myself. And I will, for later consumption, I will just recall this. So somehow you have the fact that this disconnection time is of the form n to the 2d, 1 plus little o of 1. And the time to cover the 0 floor of the cylinder is also of this kind of behavior here. All right. Now, you may start to wonder, okay, this is all very special. So my kind of torus is very regular. So is it just an accident? So here, let's replace the base by a kind of finite graph, Gn, with a large size. And there is a conjecture of Beniamini, which is saying that if the number of sites in Gn tends to infinity, and the Gn have bounded degrees, so there is a universally bounded number of neighbors for everyone. So in fact, the Tn, the disconnection time, should behave like the number of sites in Gn to the power 2 plus little o of 1. So here, so the case in the theorem with Amir Dembo and myself, you have n to the 2d, so n to the d is the number of sites in Gn. So this is indeed a situation where this conjecture is true. And in fact, in a theorem of 0.8, I proved the result showing that there is meat to this conjecture in the sense that there is an upper bound on Tn which is in that generality, and the lower bound holds for many examples. Now, I don't want to discuss here what many examples are because it's not the goal of my talk. I don't want to talk about it. I want to talk about something which is a rather arcane or subsidiary issue, which is, well, let's go back to this star relation, and do you need the little o of 1? So it looks very arcane. Why ask such a question like that? Well, one reason is that if you are able to answer that question, then your insight into the disconnection will be much deeper. Why? Because if you take this silly guess, which is the time to disconnect to cover the zero floor, well, definitely there is a need here of a little o of 1 because there are logarithmic corrections which are implicitly flying there. So for this Tn, does one need or not a little o of 1? So we are going to try to improve on star. And to improve on star, you want to have some understanding of what's the microscopic picture which is produced by random walk on these huge cylinders. Now, here is something that may be paradoxical for some of you. The small window in the cylinder is going to be I should say, for convenience now, I've switched d, in fact, to d minus 1. And so I'm going to be heading to here a d which is at least bigger or equal to 3. Before d was bigger or equal to 2, my case of interest. Now it will be d bigger or equal to 3. Now you want to have here, to improve on that question, you want to have a better understanding of the microscopic structure left by the walk. And this microscopic structure here is going to look at a window, and the window will correspond to an infinite ZD. So that may shock you in some sense, but the infinite space in this business is in fact the microscopic guy. And whereas the macroscopic guy is this kind of cylinder here. Okay. It's maybe shocking if you see that for the first time, but one can get used to it. Took me a couple of days, but now I recovered. And all right, so we are going to construct that model, and that will be the random interlacement. So the model which is going to be the base here is going to be this random interlacement. It will not be exactly what the walk is leaving, but it will be a kind of model which will be translation invariant, which will somehow be the building brick to describe what's there. What is this picture there? Okay. All right, so to explain this random interlacement, I need to give you a few crash course, no, not recall some notations about potential theory. And essentially what happens is that if you have a k which is a finite subset of ZD. So you have an important quantity which is the equilibrium measure. And the equilibrium measure is a measure which is sitting on the boundary, on the interior boundary of K. And this equilibrium measure, which is EK here, essentially has a value at each site here, which can be expressed as the probability that a random walk moves away to infinity and never comes back to K. So this is this H tilde K. So the walk will move away to infinity without ever visiting again K except for its first point. And the total mass of this equilibrium measure is the so-called capacity. So this is cap K, the capacity of K. All right. So we are after this description of that kind of idealized picture in a microscopic window. And we are going to have a wish list. So what our wish list is going to be is we are going to look for a kind of random configurations of trajectories. Now, here there is something which is called Poisson point measure. Essentially, what will happen is that if I draw here the space which is W plus, so these are trajectories, so it's an abstract door. It's nearest neighbor trajectories on ZD. So you are going to look for random configurations of points here, and which will have the property that if I take a region A of space, well, the number of points, and each point is a trajectory in A, is a Poisson variable with a certain parameter lambda A. So what that means is that if I call NA that number, it means that the probability that NA is equal to K is equal to e to the minus lambda A times lambda A K, lambda A to the K divided by K factorial. Now, the other thing which this kind of distribution has as important property is that it's very simple in the sense that if I take another region which is disconnected from A, well, what happens in A and B is independent. Now, once you have that, the only thing that you need to know are these numbers A, lambda of A, for each region. And it turns out that they are described as lambda of A is of the form M of A, where this is a measure, a sigma finite measure on this space of W plus. So what we are looking for, and this is coming out of considerations and certain algebraic identities for the walk on the cylinder, we are going to look for a family of such random configurations of points, and points will be in fact trajectories, and which will be indexed by all the finite subsets of ZD, and U, which will be a parameter. So if we keep U fixed, here are the two constraints that we have. The first is that the mu Ku is going to be a Poisson point measure with intensity. So this is the so-called intensity measure. So the intensity will be the distribution of a random walk which is starting with initial distribution, the equilibrium measure of K. So it means that it's starting on the boundary of K with these weights that I have explained before. And then there is a certain relation which is saying if I vary K, how are these different random configurations related? And what happens is that there is a sweeping relation, which is saying that if you have k contained in k prime, well, you can reconstruct mu ku in terms of mu k prime of u. And how do you do? Well, you take all the configurations, so all the trajectories which are somehow here in the support of mu k prime u, so there's w prime 2, and w prime 3. And you look at those who are going to, at some point, come into k. And what you do is that you just look at the trajectory for from the first time it enters k, and then you follow it step by step. So this is this W1. For W1, life starts here, and then it's following the move of W prime 1. W prime 2 here gives rise to this W2, and W prime 3, I mean, and W prime 2 is never entering K, so it does not contribute. Okay? So mu Ku is swept by mu K prime u. Now here I just want to make one point, because people usually have a little confusion there, which is the fact that the typical order, so if I take K prime and K here as boxes, the typical order of magnitude of the number of trajectories which are in mu K prime u is something like u, so that's the u from here, and here it's something like the capacity. So it's not growing like the volume, it's not L prime to the d, it's L prime to the d minus 2. And here, similarly for k, it's an order, the number is of order of magnitude u times L to the d minus 2, where L is the side length of k. Now, I want to stress out that there is a strong relationship between all these different measures. In particular, if mu k prime u is 0, if there is no one here, so in the smaller box, there is no one as well. So there is a strong dependence. So now, as I said, this is the kind of wish list that we have in order to construct. And this is a priori a difficult problem. But it turns out that there is a simple solution to that complicated looking problem. And as often in mathematics, in fact, you obtain the solution by going to a more complicated space on which you are doing a simple construction. So what's the more complicated space? Well, we are going to use a state space which will be slightly more involved than this space W plus of trajectories. And let me explain that. So this space here is obtained by looking at bilateral trajectories. So they are first, so they are indexed by z and not by the natural integers, and which are tending at infinity, at plus and minus infinity. And the state space you are going to look at is W star, which are trajectories modulo time shift. So we are going to forget the notion of origin of time. So there won't be a natural origin of time. Now, so you have a natural projection which to a real bilateral trajectory gives you somehow its equivalence class here. Now what happens is that there is no coherent way, no natural way to reconstruct a natural bilateral trajectory out of a class like that. So on the other hand, you can work in local charts. And what are the local charts that you are going to use? Well, you are going to take a finite set K, and the finite set K is going to be of use for you to generate a kind of common event for a class of trajectories. It will be trajectories which have entered K at some point. And for these trajectories, you can synchronize clocks by just saying time 0 is by definition the first time ever you are in K. That creates for you a kind of lift back to W. You can select coherently on this W star k a common clock. And so in some sense here you have a bundle structure on this kind of discrete space, but this is not so relevant at the moment. But what happens is that you can use these local charts to create a measure which will be the intensity of a Poisson point process on this space W star. So this measure nu is going to be such that if you read it in, so if you look at a local chart, so you restrict it to this kind of good domain, and you look in the local chart at what this measure is, so that's this qk, well, you obtain a measure qk which is on trajectories which enter k at the first time at time 0, and which has the property that its position at time 0 is distributed as the equilibrium measure. So this is this ek I was talking about. And if you fix the position at time 0, what happens? So what happens afterwards and what happens before is independent. And the forward motion is just a random walk starting from the point x. And the backward motion is looked in the backward direction is a random walk conditioned never to enter k after time 0. So this somehow is related to a similar type of measures that were considered in the 60s by Hunt, that was launched by Hunt there. They constructed such measures using projective limits. And in fact, here, the construction is just as a kind of a differential geometry type construction. It's by working with local charts and seeing that these various expressions somehow match up. So you see these expressions, these qk, live on different kind of space. In particular, they live on trajectories which for the first time enter k at time 0. But when you vary k and you go to the W star, you obtain a coherent measure. That's nu. Okay? So there is a miracle here which is happening. And that gives you this nu there. So the nu is going to be something where instead of working with W plus, you are going to work with W star. And you are going to use as, for A, the parameter lambda A is going to be of the type U times nu of A. So this is what comes now. The canonical space for random interlacements, it's Poisson point measures on W star product R plus. And the intensity measure is going to be nu product du. And your configurations that you are going to look at, it's these bilateral trajectories modulo time shift and some labels which are going to be having to do with the u. And what will happen is that in the initial problem you were looking at, mu ku, is going to be obtained by sweeping on k somehow these kind of point measures, so where you are going to take on the omega all the trajectories which have a label here which is less or equal to u. So this is solving the problem that I had indicated, and a remarkable kind of property is that the P that you obtain is both invariant under time reversal and by translation by constant. So you have this kind of translation invariant model I was talking about, and also you have for free the fact that invariant under time reversal. Let me just stress out that, you see, if you look at things in the local charts, the measure you have is not at all invariant under time reversal, because the forward motion and the backward motion viewed from that point here are very different. This is just usual random walk. This is random walk conditioned not to enter here. However, by going to this quotient space, in fact, you recover the internal symmetry of the measure which is there. Okay, so you have this structure. And in fact, this can be generalized to very general space where you are looking at tangent weighted graphs, and that has been done by Teixeira in a work which has just appeared now. So this is a very general kind of construction that you have. Okay. Now, the random interlacements, these things that you are going to look on the picture, they are just obtained by taking the range of these trajectories with labels which are less or equal to u. And the vacant set, so it's just a complement in ZD of these interlacement set at level u. Now, from this Poisson property, you have the fact that the probability that the vacant set contains a certain k is e to the minus u times capacity of k. So it's a fundamental relation, in fact, to describe this random interlacement. And if you specialize that to k, which is made of just one point, you obtain the fact that the probability that 0 is not in any of these trajectories with label less or equal to u is e to the minus u over g of 0, and g of 0 is the green function with pole at 0 evaluated at 0. So in particular, you have the fact that as you let u go from 0 to infinity, so you have the fact that when u is 0, you have 1, so essentially there is no trajectory, so everything is vacant. And when you let u tend to infinity, well, everything is occupied, so this becomes 0 here. So the kind of set, the interlacement set has an increasing density which goes from 0 to infinity, to 1 in terms of density, as u goes from 0 to infinity. Out of this, you can also obtain a kind of a calculate covariance or correlations, and you have the fact that there is a strong dependence between what happens at a point x and at point y. There is a decay, but the decay is just polynomial in the distance. So this is an important property of this kind of random set, which makes it hard to study because there is long-range dependence in it. Okay. Now, this random set I use, so the random interlacement, you can think of it as a piece of cloth. And as you let u increase, you are putting layers and layers. Think of a seamstress with using thread and putting more and more pieces of threads into a fabric. A remarkable property of this model is that IU is an infinite connected subset of ZD. So it's a piece of cloth. It's not several pieces. And it's ergodic. It's not only translation invariant, but it's ergodic. And the way you prove this is related to a celebrated theorem of Burton and Keene going back to 1989. However, there is one severe problem, which is the fact that the model violates the so-called finite energy condition. What that means is that if I show you a picture with a question mark here, so this is 0, and I know there is something here which is occupied and finite, and here there is some kind of infinite line going there, well, I know immediately that there must be something there, because there is no finite piece dangling out in this random interlacement. It's coming by these infinite bilateral trajectories, so you don't have a little piece hanging out on its own. So this makes this measure break this energy, finite energy condition. If I show you the outside of 0, I know what's in 0. Okay, so let me come back on this business. So what's this random interlacement and simple random walk have to do? So what I'm going to do is I'm going to go back to the cylinder, and I take a finite number of windows, and I have my random walk. Here is the horizontal component, y, and this is the vertical component of that random walk. And I started uniformly at level 0 on the cylinder. Now, I need to look at several quantities, which is, well, there is this ln of z. It's just the number of visits of the walk to the level z, the height z, for the vertical component. So it's the local time of the vertical component at z. And there is this thing here, this being, which is essentially a device which is keeping track of what's the local configuration put by the random walk in the window which is centered at one of these xi. So here I'm just taking the set which is visited by the random walk up to time n. I subtract x, and I take the pullback of this on zd plus 1, so that I obtain a configuration here. So it's the indicator function. I have a configuration of 0 and 1 on zd plus 1. So it's life viewed from the center, which is xi, which I'm going to look at. And then there is a certain being, which is the so-called Brownian local time. So essentially, in a kind of renormalized way, it's the time up to time t that Brownian motion spends at level v on R. Now, of course, it spends 0 time. So this has to be understood with a grain of salt. But it's a kind of quantity that you can renormalize from this, and going to the continuum, you obtain these Brownian local times. So it's something which is a certain increasing, random increasing functional with t. And of course, it's going to be giving you a kind of measure by taking the differentiation of this increasing functional. And the support of that measure is something which has 0 Lebesgue measure. In fact, it has Hausdorff dimension 1/2 on the time axis. Okay, so now what's this relationship of these random interlacements with the random walk on the cylinder? Well, what you do, you take m windows, and you suppose that the centers of the windows are tending to infinity with n, and you suppose that the height at which these windows are centered are stabilizing in scale nd at this vi. So vi are deterministic numbers. And you have times which are random times, but still, if you renormalize them, so if you look at them in scale n to the 2d, they are tending to a constant. So they can be random, but still, in principal order, in time n to the 2d, they tend to a constant alpha. So what you want to understand is these are the pictures left by random walk in the various windows by time tau n, in the window 1, window 2, window m. And you keep also track of this kind of rescaled time spent by the vertical component of the walk at time tn at level z1, which is the height of x1, and so on, and at height zm, also at time tn, and you divide by nd. So the statement is that this has a limit behavior, which is this vector, random vector phi1, phi2, phi m, u1, u2, um. And what's the structure of this? It's that, in fact, if I fix the values u1, u2, um, these variables here, which are laws on configurations on zd of zeros and ones on zd plus 1. So they are independent, and they have a distribution which is that of a random interlacement with parameter which is given by these second components which are here, these last components, so u1, u2, un. And these U1, U2, UM, you have their law, which is described in terms essentially of these Brownian local times. So what's the moral of that? The moral of that is that, in essence, so this theorem is telling you that in the large n limit, if you give yourself this kind of number of visits at the centers of these windows by, at the height of the centers of these windows by the local time, so rescaled by ND. So essentially the pictures you obtained are independent. And they behave like this kind of random interlacement that I've talked about. And the parameters are these last components. The relevant parameters are these last components. And on top of that, these last components, as should be, they have a limit law which is expressed in terms of these Brownian local times. So this kind of results have been generalized by a PhD student of mine, David Windisch, and he has obtained similar type of results for a simple random walk on the torus, CD, also simple random walk on cylinders with kind of general base where locally the base starts to look like a certain infinite graph in certain points. Okay, now this theorem here is telling you that if you are looking in the cylinder and you take a small window, what happens here starts to look like this random interlacement. Now, our initial problem is to know whether we have disconnection or not, whether we have some kind of possibility to draw a path from top to bottom which does not meet the walk. Now, this question of having a path which is avoiding the walk should have something to do with, well, in such a window, is there a possibility to draw a path which avoids the trace there? So you go to the limit, you think in terms of this random interlacement, and then you are starting to ask the questions for random interlacement. Well, the fabric that you have considered, is it a fabric which is blocking or not? So blocking in the sense of being rainproof, water cannot go through. So this is somehow here, you have blown up your local picture into an infinite z d plus 1. And now you want to know whether you are in a situation where the material that you have here is blocking or not. So can IU be a rainproof fabric? So to investigate that, what you do, you look at eta of u, which is the probability that if you start in 0, you can find a path going to infinity which remains in the vacant set at level u, so which does not meet I of u. So it's kind of a soft result, knowing this ergodicity, that having eta of u positive is equivalent to the fact that this vacant set percolates as an infinite connected component somewhere. And you can also, still going on for the soft stuff, you can, by wishful thinking, introduce a critical parameter, u star, which is the first time where this probability of having an infinite path starting from 0 becomes 0. Why not? So you can define that, and you obtain a quantity which is somewhere between 0 and infinity. Now, where it's not soft is the question, is u star non-degenerate? And there you have the following result, which came out of these two works. So first in a paper of mine from 07, and then the second thing by Vladas Sidoravicius and myself 1 year later, well, where it has been shown that u star is finite in all cases. So it means if you pile up more of this stuff, you become blocking. And not only that, you have the fact that u star is positive. So in the first paper that was shown for dimensions which had to be bigger or equal to 7, and with this paper we were able to extend it in all dimension 3. So, and for small u, in fact, this vacant set percolates in planes. So what you have is a situation where u star is always non-degenerate. You have a situation where somehow the seamstress is starting with a thread, and at the beginning it's a kind of piece of cloth which is leaking, so it's letting water go through, and after a certain range, well, after a certain level u, well, the piece of cloth that you have created is blocking, so you cannot have water go through that material. So it's a kind of amazing property of this measure that you have this non-degenerate kind of behavior. So here let me try to show you, I don't resist the pleasure of showing you. Here, what I'm showing you is somehow I'm looking at, so this is a simulation of David Windisch, and here I have the slice at mid-range here, which is just horizontal, and the black part is just this kind of IU part, so it's the occupied stuff. And the red is the largest vacant component which exists in this cube. And the blue is the second largest vacant component in that. Okay? And here it's already almost blocking in a two-dimensional slice, but as you see, it's not at all blocking when you take the three-dimensional. So, so let me just try to show you what happens now when I let u increase. So as you see here, so this is getting denser and denser here. And here you see this is the second component, which is here, and that's the first vacant component. You see there is an interesting structure which is coming at the edge. And somehow when we are going to get to u close to 3, something interesting will happen. So you see the second component here is still pretty small compared to this one. And now when we come close to 3, there is that jump. Okay? So this is related to this kind of transition I was talking about. Okay. So okay, so another question that comes here is the question to know whether this vacant component here is infinite vacant component is unique or not. And it has been shown by Augusto Teixeira that in fact it's unique. So this is again something which is related to this celebrated paper of Burton and Keene, but it's even more intricate than in the case of the random interlacement to be able to somehow overcome this this violation of the finite energy condition. And as a consequence of that, the function eta that I mentioned before, this probability of having a connection from 0 to infinity, is something which is less continuous, non-increasing, with only one possible discontinuity at u star. So it's something that looks like this. Now, among the interesting problems is, in fact, so in theory, there is a possibility of a jump. So, but one of the questions, is there a jump? And probably no. Another interesting question here is the slope finite or not? And the answer is probably yes. So these are part of tricky issues about that model. Okay, so now all that is very nice, and I've taken you on a tour, random interlacement, and disconnection, but what does that have to do with disconnection? I have to come back to the problem I started from. So here I'm going to come back to random interlacements and the disconnection time. So I'm going to look at first an upper bound on Tn. I'm going to introduce a second kind of critical parameter, U double star. And this U double star is somehow the kind of level of U such that the probability here to have a vacant connection from a box of size L to the complement of the box of size 2L, as drawn here. So this is going to have at least some polynomial decay in L. So this is somehow the mathematical formulation of that. And the proof of U star finite is good enough to show that, in fact, the U double star is finite. So it's creating, for some level, a kind of polynomial decay from that quantity. And you have this situation where U star is less than this U double star, less than infinity. It's an important question. I'll mention that later, whether, in fact, the two are equal. All right. So now, what about the upper bound? Well, the idea somehow is that if your random walk in small windows creates a structure which is kind of a random interlacement, well, if the random interlacement starts to be in a really non-percolative mode for the vacant set, so it's going to block anything. So this is somehow here, the result is saying that asymptotically, so in the large n regime, Tn over n to the 2d is less than a certain, in distribution sense, is dominated by a certain random variable which can be expressed in terms of Brownian motion. So it's the first time alpha where somewhere at some level on the line one of these local times is going to be, so these renormalized local times is going to be above U double star. Now, these parameters here, if you somehow have that still in mind, are essentially the parameters which corresponds to piloting what happens in a local window at a height which is renormalized V left by the random walk. So you are saying here that if somehow, if your local parameters get above the level U double star, then this is this zeta of U. So in picture, you see here, this darker part is supposed to represent the fact that there is a thickening, and the thickening is such that you have created a piece of material which is somehow rainproof. So this is the essence of that kind of, the intuition behind this, at least the picture for this upper bound, certainly not the proof. And as a result of that, you have the fact that Tn over n to the 2d is something bounded in a stochastic sense. So it's something which, if I can bound by a constant with a probability as close as I want to 1 if I take the constant large enough. One interesting feature is that the random variable here, which comes here in the limit behavior, is something which is in some sense computable. So this has been done by Borodin and Eisenbaum. So you can calculate the Laplace transform of these random variables, where you have this expression which is coming here, with here the modified Bessel function which comes here. Well, you have also lower bound on Tn that can be derived out of this. So there was a previous result of Amir Dembo and myself saying that if the dimension is large, at least 17, well, n to the 2d divided by Tn is tight. So it means it cannot be too big. It means that Tn must be somehow bigger than a small constant times n to the 2d. So this was a lower bound on Tn, which had the disadvantage of working only for high enough dimension. And in fact, with random interlacements,
there is a way to use a kind of asymptotic lower bound on Tn divided by n to the 2d, which is somehow as a lower bound in terms of a multiple of the random variable I was talking about. So u is small. Before it was u star star. Now it's zeta of u. By scaling, it's something which in distribution is a multiple of the same distribution. So in the large n regime, Tn over n to the 2d is quenched by two levels of the same distribution. And in particular, you have the fact that you have this tightness, which is there. So to come back to the initial question, so in fact, Tn lives directly in scale n to the 2d, and this is not necessary. Now, this kind of result here, this upper bound and this lower bound, motivates a number of questions. So from the pure percolative point of view, there is this question of, is it the case that u star and u double star agree? So it's something which is known to be true for usual Bernoulli percolation. Here, this is a rather tough cookie for that model because of the long-range dependence which is there, and also because there is one of the key inequalities of percolation, which is the Vandenberg-Keston inequality, which is not available due to this long-range dependence. Now, I've given you an upper bound and a lower bound for this Tn over n to the 2d. Well, in fact, this strongly suggests that this Tn over n to the 2d, if things are right, go to this zeta of u star, which is meaning that somehow the system is at disconnection is just propagating itself in a kind of critical mode. So this is what physicists sometimes nickname self-induced criticality. So here, by looking at disconnection, you are creating a kind of mode for the random walk where, viewed from the percolation point of view, it is creating a picture which is critical. So that's part of the question. And of course, here, this strongly suggests that one should be able to say something about where disconnection happens, because it has to happen where somehow you have a thickening on the picture, and that should be also describable in terms of local time, Brownian local time. A quite interesting question is to describe what is this picture that you see from the point of disconnection. This is this kind of fine, chiseled kind of being that I've shown on the simulation, and that should be related to some kind of percolation cluster at criticality, so it would have to come under a certain conditioning. So for this vacant set. And then there is the question of universality, so how general is that? And another kind of question I did not speak about, because I just spoke about this kind of cylinder. It's this, what we have been talking about is somehow this kind of being where random walks are in models which are large recurrent structures which locally look like transient, infinite transient graphs. And there are some, you can look at that, for instance, by looking at random walk on the torus, and at U star it should be a situation where it makes the difference between there is a giant, a large vacant component or not in the complement of the range of the random walk. And one of the issues at stake is there something which is mimicking what happens on the model of the random graph, where there is a kind of so-called of double jump. So there is a mode for u less than u star. U bigger than U star, and that U star there is another kind of scaling which is coming. So these are just some examples of these questions, and I think my time is up, so I'll stop here.